Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq Hamzah bin Ayub. My matric number is 1913125996 from RY55. I will presenting about a project of mounting bracket for subject MMK 21103 Computer Aided Engineering. In this video, I will presenting about introduction and methodology for linear static analysis. Introduction. In this project, we will investigate the technical case of a new geometrical design of a mounting bracket to support a post. The material of the mounting bracket for the research is aluminium alloy 7075T6 with a yield strength of 476 MPa. The selection of the material is based on the weight and the performance of the material that is able to withstand in an open environment. The design of the bracket will be done using two software, which is SolidWorks and ANSYS. This is the drawing of a mounting bracket. Next is methodology for linear static analysis. The first step is open ANSYS software and select static structural. Second is rename the title of the analysis, then save the file. And then select engineering data and add a material, and then drag isotropic electricity into the set material and set the value of Young modulus and Poisson ratio. And then open geometry and select new design modular geometry. Then set the unit to millimeter and import the external geometry file. Then close the design modular and select model. Rename the model to bracket and select the material for the bracket. Set the mesh as a tetrahedral element with the size of 3.0 mm. Select the specific type of support for the bracket, for example fixed support, and then apply load for the bracket, and lastly set the solution for the bracket, for example equivalent Vomiser stress and total deformation, and then finish. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Lokman Hakim bin Shamsul Fazli from RY55 Machining with metric number 1913125990. Today I would like to present about thermal stress analysis. What is thermal stress analysis? Thermal stress analysis is necessary to evaluate the amount of wavage caused by thermal strain and to prevent failure due to excessive stresses caused by thermal conditions. As we can see, this is flow chart for us to make or to do or to create the thermal stress analysis using ANSYS.
Assalamualaikum, my name is Adin Sydney from RY55 with metric number of 1913132234. I will be presenting about project computer aided design. I will be presenting about methodology of free vibration. First in the methodology, open ANSYS software and select model. Rename the file of analysis. Save the file. Next, select engineering case and add a material. Drag isotropic elasticity and set the material and the value of Young modulus and Poisson ratio. Under the physical properties toolbox, drag density into the set of aluminum alloy. Open geometry and select new design modular geometry. Set the unit into millimeter and import it to the external geometry file. Close the design modular and select model. Use material tab, select aluminium alloy 7075 T6 as material for the part. Select set the mesh as tetrahedral element with the size of 3.0 mm. Click support and choose specific type of support to be used. Rotate the model by clicking and holding the mouse. Select the surface of the hole to be constrained and click apply. After finishing that, right click solution and solve. Finish.
Back to me again. I'm Lokman. I would like to present about result for this project. The first part is linear static analysis. The maximum value for equivalent stress is 180.35 megapascal plotted on red color counter, and the minimum value for equivalent stress is 0.064299 megapascal plotted at blue color counter. For total deformation is the maximum value 1.3543 mm plotted on the red color counter, and the minimum one is 0 mm plotted at the blue color counter. The second part is thermal stress analysis. The maximum value for equivalent stress is 234.53 megapascal plotted on the red color counter, and the minimum one is 0.06429 megapascal plotted at the blue color counter. And for total deformation, maximum is 1.3737 mm plotted at red color counter, and the minimum is 0 mm plotted at blue color counter. And the last part is free vibration analysis. There are 5 total deformation and mode in free vibration analysis. Mode 1, simple bending. The maximum value of total deformation recorded in 91.766 mm with the frequency of 204.59 Hz. Mode 2, transverse bending. The maximum value of total deformation recorded is 97.624 mm with the frequency of 246.65 Hz. Mode 3, bending at middle span. The maximum value of total deformation recorded is 123.88 mm with the frequency of 1554.4 Hz. Mode 4, twisting. The maximum value of total deformation recorded is 116.7 mm with a frequency of 1624.7 Hz. Mode 5, bending at quarter span. The maximum value of total deformation recorded is 123.92 mm with a frequency of 2769.2 Hz.
Next, I will be presenting about discussion. First discussion is linear static analysis. The maximum stress 108.35 megapascal plotted with red counter at the base of the bracket, and the maximum total deformation is 1.3543 mm. This is a proof that the maximum deflection is below 1.5 mm, below the benchmark value given. The result of this linear static analysis can be achieved as the CAD model of the bracket is designed according to the criteria that is given. Following this criteria, the bracket design is modified to suit the requirement. Next discussion is the thermal stress analysis. What can be observed from the figure is the maximum total deformation is 1.3543 mm. This is a proof that the maximum deflection is 1.5 below the benchmark value given. The red contour in the figure indicates a high level of thermal stress as the main load is the red contour section. That's why the front end of the structure is red, showing a high number of thermal stresses. On the other end, at the blue contour shows that a lower thermal stress is shown. Next discussion is the free vibration. In free vibration analysis, there are 5 types of total deformation, which is total deformation that represents deformation for mode 1, which is simple bending. The maximum value of total deformation recorded is 91.766 mm with the frequency of 204.59 Hz. Total deformation 2 that represent deformation for mode 2, which is transverse bending. The maximum value of total deformation recorded is 97.624 mm with the frequency of 246.65 Hz. Total deformation 3 that represent deformation for mode 3, which is bending at middle span. The maximum value of total deformation recorded is 123.88 mm with the frequency of 1554.4 Hz. The total deformation 4 that represent deformation for mode 4, which is twisting. The maximum value of total deformation recorded is 116.7 mm with the frequency of 16247 Hz. The last total deformation, which is total deformation 5, that represent deformation for mode 5, which is bending at quarter span. The maximum value of the total deformation is recorded at 123.92 mm with the frequency of 2769.2 Hz. The advantage of this vibration analysis include the detection of the mechanical issues such as worn bearings, imbalance, coupling, and bearing misalignment by measuring the amplitude and the frequency of vibration. Lastly, I will be presenting about conclusion. The conclusion from this analysis: it is possible to use finite element method in order to solve real engineering problems. The analysis through the use of finite element method enables a more efficient ways to solve problem with the aid of precise diagram of actual object. The maximum and minimum value for any result, such as temperature and total heat flux, also can be determined with the color contour and location also is labeled as well. The ability to analyze three-dimensional problem of mechanical structure, such as heat transfer analysis. Therefore, the objective is achieved for this project session. Improvement of that can be done are such as improving the heat transfer in such parts by raising the temperature difference between the object and the zone ring, improving the coefficient of convective heat transfer, and expanding the body surface area. Thank you. That's all for me.